my course name is Electronic Device and Circuits, and it is Unit 2, which is a diode applications, name of the Unit 2. And the topic for today lecture is bridge rectifier operation, derivation of parameters. Okay, the overview of my presentation will be like this. First, I will be saying about the operation of the bridge rectifier, and then I will be discussing about the derivation of the parameters related with the rectifier, and finally I will be recapping the things whatever I discussed. And the textbooks referred are, as you can see, Jacob Millman. Title is Electron Device and Circuits, and other is Jacob Millman, and the title is Electron Device and Circuit Theory. Others are Bollisted and Nashelsky. And finally, third book is Electron Device and Circuits by Salivahanan and Suresh Kumar. So, in the last classes, we discussed about various types of rectifiers. First type is the half-wave rectifier, second type is the full-wave rectifier, and an improved version of the full-wave rectifier, that is nothing but a bridge rectifier. So, why you go for bridge rectifier in spite of going for the full-wave rectifier, where we are using two diodes? So, main advantage of going for bridge rectifier is, as you can see, here we are making use of a conventional transformer here, okay, whereas in the full-wave rectifier we use the center tap transformer, which is an expensive affair. So, that is why here we won't go for the center tap transformer, here we go for the conventional ordinary transformer. Okay, that is a main change that happens here when compared with full wave rectifier. And also the peak inverse voltage for a diode is also reduced here. That we will be seeing later while deriving the parameters. Okay. So, now let us go for the operation of this particular bridge rectifier. As you can see, this is a circuit diagram of bridge rectifier, and here this is the AC input. The rectification is nothing but conversion of AC signal into a DC signal. So, that is why here input will be AC input, which is 220 volts AC with a frequency of 50 to 60 Hz. That will be the input here, and here we are making use of a transformer which is not a center tap. And here only one thing, the change here is we are going for a 4 diode arrangement in the form of a bridge. As you can see, D1, D2, D3, D4, they are connected together in the form of a bridge. So, 4 diodes we are going for. One is called as a D1, D2, D3, D4. Okay. So, and this is a load resistor RL, across which the output voltage will be taken. Okay. So, this is about the circuit arrangement, and this is a primary winding where we are providing the input, and this is a secondary winding for which we are connecting a 4 diode arrangement in the form of a bridge. Diodes are D1, D2, D3, D4, and this is a load resistor across which the output voltage will be taken. Okay. So, let us assume that we are providing the input AC input voltage. Whenever you say that it is an AC input voltage, we will be treating it as an AC wave, a sinusoidal signal. As you can see, so from 0 to pi it comes under the positive half cycle, and pi to 2 pi it is a negative half cycle. So, this is a total cycle consists of positive half cycle where omega t is in between 0 to pi, and negative half cycle when omega t is in between pi to 2 pi. Okay. So, here we are providing this input voltage, which is an AC voltage. So, let us separate into 2 periods. One is, first period is whenever omega t is in between 0 to pi. Whenever omega t is in between 0 to pi, what happens here? This particular terminal, this becomes positive when compared with this terminal. Okay. This becomes positive when compared with this terminal. Okay. And during the negative half cycle, what happens here? Just it is the inverse of operation which happens when omega t is in between 0 to pi, and this terminal becomes negative and this becomes positive. Positive in the sense more positive, minus sign means less positive. Okay. So this is the about the circuit arrangement. Whenever you are providing AC input voltage, whenever omega t is in between 0 to pi, the terminals polarities will be changed, and this operation can be seen more in a close manner in the next slide like this. Okay, colorful slide which is taken from the Google. So during the positive half cycle, I said positive half cycle in the sense this part, when omega t is in between 0 to pi, what happens here? This terminal A becomes more positive when compared with B. Okay. So here we are providing the AC input. Terminal A becomes more positive when compared with B. Now let us check the status of all the diodes. Status in the sense what happens to the diode, whether it is forward biased or reverse biased. So let us check the diode D1. As I already said, this A is more positive and this one is the anode. Anode is more positive means what happens to diode D1? This must be forward biased. And what about the status of this diode D2? So as you can see, this is the cathode. Cathode is more positive. That means this diode will be reverse biased. Okay. So diode D1 is forward biased and diode D2 is reverse biased. So the current, the diode D1 will be forward biased means it will be conducted and the current will be flown in this manner. And as you can see here, the load resistance RL is connected here and the current will be flown like this. And what about the status of diode D3? Let us check here. So as I already said, during the positive half cycle, A is more positive when compared with B. B is at lower potential. This B is connected to cathode of diode D3. Whenever cathode is at lower potential, then we can say that this particular D3 is also forward biased. So what happens here? The current will be flown through this diode D3 which is forward biased. Okay. So this is the current flow whenever the provided input voltage is in the positive half cycle, whenever omega t is in between 0 to pi. This A is more positive when compared with the B. Whenever A is more positive when compared with B, D1 will be forward bias, D2 will be reverse bias and D3 will be forward bias. And what about D4? As I already said, B is at lower potential. Lower potential means lower potential is connected to anode. What happens to this diode D4? This must be reverse bias. Okay. So D2 and D4 are reverse bias and D1 and D3 are forward bias. So we can draw the flow of current like this. The flow of current is happening due to the forward biasing of two diodes, diode D1 and D3. So that's why here I am drawing the direction of the current, conventional current like this. So first it is passing through the diode D1 and it is flowing through the load resistance RL through this diode D3 in order to move to the ground. Okay, this is the direction. So by which whenever current is flown through the load resistance RL, a voltage will be developed across the load resistance RL. So that is nothing but V0. The output voltage is represented as V0. As you can see here, this is 0 to pi, positive half cycle. So what is happening here? Output voltage and output voltage is developed across load resistance RL. Okay. So this is a discussion whenever omega t is in between 0 to pi during the positive half cycle. Okay. So during the positive half cycle, D1 and D3 are forward bias and D2, D4 are reverse bias, by which the current will be flown through the load resistance RL, by which an output voltage will be developed, as you can see here in this diagram. So positive half cycle and output voltage is developed. Okay. Next, during the negative half cycle means, as you can see, whenever omega t is in between pi to 2 pi. Okay. So what must happen here? This terminal must be negative and this must be positive. So in this diagram easily we can understand that. So whenever during the negative half cycle, whenever omega t is in between pi to 2 pi, that means this is 0, this is pi and this is 2 pi. Pi to 2 pi, it is called as a negative half cycle. So during the negative half cycle, what happens here? A is negative and B is positive. That means B is at higher potential when compared with A. Now let us check the status of 4 diodes. What happens to diode D1? What happens to diode D2, D3, D4? Okay, as you can see here, first let us check about D1. So A is at lower potential. Lower potential is connected to anode. That means this will be reverse bias. Okay, A is at lower potential. That is connected to cathode. That means this must be forward bias. Okay, so what about the B terminal? B is more positive. So B is at higher potential, that is connected to the anode of D4. Anode of D4. That means this must be forward bias. And what about D3? So B is at higher potential, that is connected to cathode of diode D3. That means this must be reverse bias. Okay. So D1 and D3 are reverse bias and D2 and D4 are forward bias. Whenever AC input is in negative half cycle, whenever omega t is in between pi to 2 pi, A will be at lower potential when compared with B. So that's why here D2 and D4 are conducted and D1 and D3 are non-conducted. Okay. So that's why here let us draw the current direction here, conventional current direction. So here positive means first the current will be started like this. The D4 is forward bias and a load resistor. It passes through the load resistance RL, and D2 is also forward bias and it will be reaching to the lower potential, that is a ground. Okay. So this is the direction of the current. So the current is flowing through RL once again. So a output voltage will be developed across RL, as you can see here. So this is the output voltage. So during the positive half cycle, output voltage will be developed, and during the negative half cycle also output voltage will be developed. Okay. So this is about the full wave rectifier, which is called as a bridge rectifier. Okay. For both cycles, the output will be generated. Both cycles in the sense positive half cycle whenever omega t is in between 0 to pi, and negative half cycle whenever omega t is in between pi to 2 pi. In both cases, the output voltage will be developed. So this is about bridge rectifier, where we are using a ordinary conventional transformer, and here we are using 4 diodes which are connected in the form of a ring. Now let us go for the derivation of parameters. Derivation of parameters, first one is as you know, the ripple factor. Ripple factor judges the performance of rectifier. Okay. So ripple factor, if you go for the formula here, already we derived, same thing happens here, same will be applicable for here also. We derived in the full wave rectifier by going for this formula. Formula will be, so here Vrms by VDC whole square minus 1. So what is the value of Vrms? Vrms is equal to Vm by root 2, and VDC value will be equal to 2 Vm by pi. So if you substitute those values, you will be getting the value as same as full wave rectifier. The value will be 0.481, which is same as the full wave rectifier. Okay. Next, the rectifier efficiency will be remained same. Okay. Efficiency also will be same, which is same like full wave rectifier. Okay. No need to discuss here. And here the transformer utilization factor, that is called as TUF. So TUF is equal to, the formula is PDC by effective volt ampere rating of transformer. So in the case of full wave rectifier, we derived the TUF by taking the TUF of primary winding as well as the taking TUF of secondary winding, and we went for the average of 2 TFs and we calculate the TF like that. But here it is a different case. So the TF ordinary derivation, like we need to go for PDC, you know the PDC value. PDC is IDC square into RL. Okay. And what about voltage ampere rating of the transformer? So this can be written as, so Vm by root 2, that is the rating of the secondary of the transformer, into what is the RMS value, current RMS value of full wave rectifier. The value will be Im by root. Okay. So IDC square into RL by Vm by root 2 into Im by root 2. So if you substitute the values here, so here I am erasing this one. So what is the value of IDC? IDC value is, for full wave rectifier, what is the value of IDC? 2 Im by pi whole square into RL by Vm. I am writing it as Im into RL by root 2 into Im by root 2. So if you go for the calculations here, so here 2 Im by pi whole square means 4 Im square by pi square into RL. So here Im is there, it becomes Im square into RL by root 2 into root 2, it becomes 2. Okay. So finally you will be getting, numerator is 4 by pi square, this RL and this RL will be cancelled, and this Im square will be cancelled. So you will be getting 4 by pi square into 2 by 1, you will be getting 8 by pi square, that is equal to 0.816. So this is about, 0.816. So 8 by pi square means, if you go for the calculation, you will be getting 0.816. This is the transformer utilization factor. And fourth remained parameter is important parameter is about the peak inverse voltage. So in the last class we had seen, while deriving the peak inverse voltage of the full wave rectifier, so we are getting the value of peak inverse voltage value is, if you refer back the lectures, the peak inverse voltage of full wave rectifiers, you will be getting it as a 2 Vm. 2 Vm is the peak inverse voltage of the full wave rectifier. 2 Vm, which is shared by a single diode. Okay. So what happens here? Let us see here. If you go for this diagram, as you can see here, total 4 diodes are there, out of which 2 diodes are becoming active and 2 diodes are non-active. Active in the sense they are forward bias, non-active means reverse bias. Okay, during the positive half cycle, what happens here? D1 and D3 are forward bias and D2 and D4 are reverse bias. So if you calculate the peak inverse voltage here, already D1 and D3 are forward bias, a voltage Vm will be developed across RL. Okay, and here input voltage, one peak voltage will be there, Vm. So total voltage which is withstanded by these 2 diodes which are reverse bias, D2 and D4, is Vm plus Vm. You will be getting 2 Vm, but this 2 Vm is being shared by 2 diodes D2 and D4. Okay, once again I repeat, 2 Vm is being shared by 2 diodes D2 and D4. So what is the PIV of each diode? So you will be getting Vm. Okay, if it is a full wave rectifier, the peak inverse voltage is 2 Vm, which has to be withstanded by the diode in the reverse bias mode. But here this total 2 Vm is being shared by two diodes which are reverse bias D2 and D4. So, what is the peak inverse voltage per diode? Per diode is Vm. So, that is why we can say here the peak inverse voltage is reduced in the case of bridge rectifier when compared with the full wave rectifier. Okay. So, all the parameters are over. First, we discussed about how to derive the ripple factor, which is same as the full wave rectifier, and second, the rectifier efficiency, that will be also same, and third, we derived the TF. TF will be different here. The TF value we got it as 0.816, and finally peak inverse voltage, that is a voltage which is withstanded by the diode in the reverse bias mode. So, in the full wave rectifier it is 2 Vm per each diode, but here the PIV will be equal to Vm. PI will be equal to Vm per diode. Why? Because 2 Vm is being shared by two diodes, that is why the PIV per diode is Vm. Okay, that is the difference. So, by this I can conclude all the rectifiers. So, first we discussed about the full wave rectifier, second we discussed about half wave rectifier, and third one is the bridge rectifier. So, you can prepare a comparison table based on the parameters, and we can study the differences. Okay, and in the next class I will be saying about the types of filters. Okay, thank you.